Hi everybody. Today we're going to talk about anonymous functions in Mathematica. This builds on the ideas of our previous tutorial where we were defining functions for the first time. Now we have a much more rich environment to do so. Before we get there though, I'd like to take a moment to talk about how I understand how to get to anonymous functions. And the way I do that is I think about the structure of functions in Mathematica. When we are working on the defining our functions, we used the notation where we did f of x underscore colon equals, and then we got the right-hand side of our function. This itself is a shortcut for using the function command. So the function command takes all of that and it wraps it into a one compact expression. So before we defined square me of the function x to be x squared. And so what we're going to do is we're going to create an alternate square me. So I'll just call it alternate square. And what it's going to do is going to be a function, and what function does is it has a list of inputs and then the right-hand side of the expression. So in this case, we're thinking of this x as the local variable and x squared as the rule that applies to the local variable. And so this here is all wrapped into one function command, and we're using the equal sign and not the colon equals here. Similarly, we'll do an alternate atom up. Remember what we had written for atom up of x comma y, x underscore comma y underscore that's going to be just x plus y. So the alternate way to define atom up is going to say take in two inputs. Here they're written in a list, even though it is two inputs. That's because function takes two input. It takes the input variables and it takes the right-hand side, the rule that's applied to the input variables. And this is the internal structure for what this alternate atom up looks like. So we can apply these functions in exactly the same way we did before. We take an alternate square of 20, and that's going to give us 400. Alternate atom up of negative pi comma 3 pi is going to give negative pi plus 3 pi, which is 2 pi. So if you wanted to, we didn't actually have to define alternate square or alternate atom up. What we could do is we could just say, hey, we are creating a function that takes in an x and gives out x squared, and let's apply that to 20. Or the same thing we could say, we have a function that takes in two inputs and outputs x plus y, and we apply it to 2006,994, and we get 8994. This feels a bit clunky, right? Why are we defining it this way? But it's going to lead to this structure right here where we think of our function as a function that takes in some inputs and gives out some outputs. It leads to the idea of an anonymous function. So let's jump right in. So let's say you want to create a function. You're only going to use it once. You don't really want to give it a name. It doesn't matter if it has a name or not. What we can do is we can create an anonymous function. They are a little weird. They've got these weird symbols in them, and they're a bit confusing here at first. But as you get better and better at Mathematica, they're super helpful, super handy. Not only that, you're going to, if you look at any code written in Mathematica online, you're going to see these pound signs or octothorpes or hashtags, and you're going to see these ampersands, and you're going to wonder, what are they? Well, this is what they are. All right, so I've tried to use a similar type of coloring to what we had before. Here, this right-hand side corresponds to the rules that you want to apply to your inputs. And this time what we have is we have the inputs are represented by this pound sign. It's called slot because it's basically the slot that we're leaving for input variables. And what it represents an anonymous input variable. So when we were up here and we said we want a function that takes in x and gives out x squared, and we plug in the number 20, well, did it really matter that it was called x? No, it didn't matter it was called x. So what we're doing here by using the pound sign is we're saying, hey, it doesn't really matter what the variable name is. We're just going to let it be pound. We're going to let it be this slot. And any input that comes in is going to get put into the slot. If your function has more than one input, then you should use pound1 or pound2. Sorry, pound1, pound2, pound3, however many inputs that you have. This ampersand, the AND symbol, represents the end of the function and signals to Mathematica that whatever comes afterward is the input to that function. And I like to put in some parentheses just to delineate what this function is. They're not always necessary, sometimes they're really helpful. Okay, so let's look at the function that squares an input. Okay, here is a function that says, whatever the input is, square it. This ampersand says this is the end of the function. And this short terminology you can just read as, take whatever the input is and square it. Just like here you could say, there's two inputs to this function. Take the first input and the second input and add them together. All right, and so when we want to apply them, we still use bracket notation, right? And we say, take the input, square it, and we're going to apply it to pi. Well, we get pi squared. If we have take input 1 and input 2, add them together, and apply it to 3, 4, we're going to get 7. All right, that's really compact notation. We didn't have to define a function. We didn't have to define the parameters. We're just saying it's a pure function. It's an anonymous function. It's one that doesn't have any of those constructs that you might think that would be like you expect to see in a function. It's just taking it down to its essence and saying, I just want there to be, I want to take a number and I want to square it. That's what I want to do. Okay, so one place where this is really, really helpful is to use it with the map command. Right, so here's the structure of your thought process. You're going through and you have in your mind a list of things that you want to do. And as you're going along, you're saying, hey, I've got this list of things. What I'd really like to do is I'd like to apply a function to each one of those individual things. Well, you could define your function and then use the map command. Or you could say, hey, wait, I'm just going to create an anonymous function that I'm going to apply to every element of the list. All right, so let's see an example here. So I've got a list of numbers. So I created a list of numbers, 4, 7, 10, 13, 16, and I'm like, hey, wait a minute. I'd really like to know what happens if I square each of those numbers. Well, I don't need to create a function that squares numbers. I can just say, I want to take this function, the function that squares things, right? This is the function that has as input, it takes an input and it squares it. And I want to take that and I want to apply that to every element of the list. Boom, look at that. I've taken this and I've added it to every element of the list. All right, so oh, here's the answer. I'm going to get rid of the answer for now. So this one says create a list that contains the regular polygons that has the number of sides given by my list. So here's my list. It has the numbers 4, 7, 10, 13, 16. So what I'd like is I'd like a square, I'd like a heptagon, a decagon, a 13gon, and a 16gon. I'm sure there's technical words for those, but I don't know them, and it doesn't really matter. So what we'd like to do is we'd like to take, so what do we want to do? We have our my list, and we'd like to apply a function to it. What does that function look like? Well, to create a regular polygon, there's actually a function called regular polygon of 4. In Mathematica, this is a primitive. This is not, you don't see it until you use the graphics command. So graphics of regular polygon of 4 creates a square, just like graphics of regular polygon of 7 creates a heptagon. So this is the rule that we want to apply. We want to do graphics of regular polygon of the number. So we're going to create a pure function that says graphics of regular polygon of the input ampersand. So that's taking in this is an application of the pure function where we say this is our input. I want to do regular polygon of the input, and I want to do graphics of that. And so what we're going to do is we're going to map this to our my list. And that's going to give us our list of regular polygons. You know, I'm realizing right now that I think that wasn't actually what I had copied out before. Let me see what I had before. Oh, it is. Okay, so that's the way you approach it. You figure out one of the examples, and you see something that's changing. That something that's changing becomes the pound sign, and then you can apply this to the list. All right, here's another example. Graph the following functions from -5 to 5. So here are some functions, and what we want is we want to graph those functions. So let's first do an initial one. Remember, that's the plot function. So we'd like to plot sine of x where x goes from -5 to 5. All right, but what we want to do is we want to apply that to each of those functions. So what did this look like? The thing we want to replace is sine of x. So we do plot of pound. X goes from -5 to 5. And this is our anonymous function. It takes in an input, plugs it in here, and it does plot input x from -5 to 5. And we can map this onto the functions. Boom. Hey, look, there's our 4 functions plotted from -5 to 5. Sine of x, x squared, arctan, and log of x. All right, one last bit. So we talked about MapThread last time, and as I was working through the examples, because I've had some experience in Mathematica, I was thinking, let's just use the anonymous functions. So now let's do that. Here's our x list, y list, and z list that we had. If we want to, let's say we had our list of coordinates. These are the x coordinates, these are the y coordinates, these are the z coordinates. And what we'd like to do is we'd like to create just the coordinate pairs so that we could see some three-dimensional coordinates. Well, we'd like to pick x1, y1, z1 and put them in a list. Okay, so what that's doing here is it's saying, let's say we had, so what we're looking at is we're looking at this function x1, x2, x3. If we put in x1, x1, y1, z1, if we put that into the function, what we get is we get a list that has x1, y1, z1. But now what we'd like to do is we'd like to do this for each triple, each corresponding triple of numbers, one chosen from x list, one chosen from the y list, one chosen from the z list, and so we need to use the MapThread function. And so MapThread says that, okay, we're going to have an input. There's going to be three inputs, a first input, a second input, a third input, and we're going to apply this, we're going to put them into a list. So we have list with x1, y1, z1, x2, y2, z2, etc. And here's an important thing to recognize. Let's make it bold and let's make it pink because we can. This is something that often you'll get an error because your lists aren't the same length. So make sure your lists of data are the same length to be able to apply MapThread. All right, so let's make this list of colorful days of the week using MapThread instead. So what do we need? We needed some days of the week, and that's going to be Monday, Tuesday, Wednesday, Thursday, Friday, and we need some colors, and those are going to be red, orange, yellow, green, and blue. All right, so those are days of the week, those are our colors. And what do we want to do? We want to use MapThread, and our function looked like what? It looked like style of the word using the color, with the inputs being the days of the week and the colors. So what we're doing is we're applying the style command to, let's make sure we've written this one out, style of Monday, comma red. This is what we want it to look like. And what we've got here is we have, this is the format. We've got the first entry is the word, and the second entry is the color. And so this creates elements of the list. It applies the style command for each day of the week and each color. So let's kick it up a notch again, where we say, all right, so we've got the days of the week and we've got colors, but let's say we wanted different fonts and different font sizes. So what you'll see in Mathematica is what we can do is we can do, all right, style Monday red. We can also do font family, and then you get a long list of things that you might want to do. So let's say we've got a times, and we have a font size, and let's make it 14. And that's going to change the font, and that's going to change the size of the font. And so let's create a list of fonts. All right, so we're going to put in times. Maybe, let's see, I don't know everything that's available, but I guess there's probably going to be Arial, Helvetica. Let's see what else we can do. Normally it'll give us some options. Why, sure, let's Allegria. I never had to say that in words. And then let's do one more. What else do we have? Algerian. So here's 5 different fonts. And then we have font sizes. Let's call it sizes. And let's say we put in 50 and 30 and 20 and 5 and 15. So here's some font sizes. So let me suppress those outputs. And then I'm going to create a new MapThread. And the style has the word that needs to be changed. It has the color that needs to be changed. It has the font, the font face. So what did that look like? It looked like font family, arrow, number 3, and then it had font size to number 4. And so we put those in here, colors, fonts, and sizes. Monday's huge, Tuesday's, Wednesday, Thursday, Friday, and there we go. All right, so that's the end of this video. Thanks for watching. Bye.